Again, I will now introduce our next speaker. That would be Paul Rebischung, under the title Terrestrial Frame Solutions from the Third IGS Processing, the IGS Contribution to the ITRF.
Thank you, Myra. Thank you very much for organizing this event, and welcome everyone. So in this talk, I'm going to focus on the terrestrial side of repro3, station position estimates and Earth's rotation parameters. To start, here's a little bit of background about repro3, which was, as Felix told you already, the third reanalysis by 10 analysis centers, this time of GNSS data back to 1994, using the latest available models and standards. And the main purpose of repro3 was to provide the IGS input to ITRF2020. A major change compared to repro2 was that this time Galileo and GLONASS observations had been processed by a majority of ACs, whereas repro2 was essentially GPS only. The inclusion of Galileo in repro3 was made possible thanks to the availability of new multi-GNSS calibrations for several ground antenna types that were included in a specific antex file called IGS-R3.ATX. On the satellite side, this antex file includes the published pre-flight calibrations of the Galileo satellite antennas. And as for the GPS and GLONASS, ZPCOs, satellite ZPCOs, they have been re-estimated based on those published Galileo satellite antenna calibrations before repro3. As a consequence, the IGS repro3 solutions have for the first time an ITRF independent scale, which is instead based on Galileo, on the published Galileo calibrations of the Galileo satellite antennas. And this independent scale could, in principle, potentially contribute to the definition of the ITRF2020 scale. Then there's a whole list of other model updates in this slide, which I'm not going to detail, but for more details and the estimated impacts of these different changes on terrestrial frame products, I refer you to IGS Mail 8026. Now, this slide shows the contributions of the different ACs to repro3. It's mainly just for the record. I don't have anything particular to say about it. So let's move to results from the daily repro3 terrestrial frame combinations. As usual within the IGS, the solutions provided by the different analysis centers were combined on a daily basis. And the daily combined repro3 SINEX solutions constitute the IGS input to ITRF2020. And they are now available at CPBIS and IGN. Here's a network of stations in the repro3 combined solutions. There are 1,905 stations there in total, with a quite nice distribution. And this network basically includes all IGS stations, plus all GNSS stations collocated with other space geodetic techniques. And finally, densification stations that were of special interest to regional reference frame subcommissions like URF, CIRGAS, etc. All stations are far from having observed for the whole time span, and the average observation span of the stations is actually 11 years. All ACs are also far from having processed the whole network, as can be seen in this plot of the number of stations in the daily AC and combined solutions. And now let's see how the daily solutions provided by the different analysis centers agree with each other. So these plots show daily median formal errors of station positions in the different AC solutions after they have been weighted for the daily combinations. So these numbers represent the level of agreement between station positions in the different AC solutions. And they are also a proxy for the weights of the different ACs in the daily combinations. The picture gets clearer if we smooth this time series of daily median formal errors. And we can see here that the overall level of agreement between AC solutions reaches steady levels of around 1 millimeters in east and north and 3.5 to 4 millimeters in up after 2004, let's say. These numbers are actually practically the same as in repro2, but unlike in repro2, there are no more ACs on the tail of the peloton. And on the other hand, we have a new frontrunner, which is TU Graz, shown in gray here, and whose solutions get more weight in the combination than those of any other AC. I think that's also the case in the repro3 orbit combinations, but so far the precise reason why the TUG solutions thus appear as more precise than anybody else's remains unclear, and this still needs to be investigated. Now, here's an example of station position residual time series from the repro3 combinations. This is St. John's, Canada, and each one of the curves represents the 1 AC minus IGS combined residual time series. So there's nothing special to report here. The stations behave quite well, but some other stations do not behave as well, like this one in Casey, Antarctica, where the problem is that there are inter-AC biases, mainly in the up component, and that these biases change with equipment changes at the station, like here in the end of 2008 and here in 2013. There are not that many stations with such clear biases between AC station position estimates. Still, I think that a systematic study of these biases would be helpful and might help to track down the origin of these biases, but that's for later. We can also look at the AC station position residual time series in the spectral domain, like here with their average periodograms for the north component. The picture is similar in east and up, and it's also similar to what we saw in repro2 with the inter-AC differences consisting of approximately white plus flicker background noise, plus draconitic, seasonal, draconitic, and fortnightly signals. The main difference with the repro2 picture is the apparition or generalization of new spectral peaks in the GLONASS-related 8-day spectral band. And note that these peaks are now larger for ACs who did not process or downweighted GLONASS. So this is a good illustration of the fact that the interpretation of these combination residuals is made difficult by the fact that the different ACs are compared to their weighted mean. So another item on my to-do list will be to make to study absolute errors in the station position time series from the different contributions to repro3. Now let's move to Earth rotation parameters. I showed here as an example the time series of export rate residuals from the different ACs and their amplitude spectra to the right. It's again a quite similar picture as what we saw in repro2, except for these large fortnightly peaks and other clusters of peaks in the GFZ and NGS ball rate residuals, which might point to some errors in implementing the new subdaily EOP tidemodel by these two ACs. But a nice result about ERPs is that the overall inter-AC agreement on ERPs has noticeably improved from repro2 to repro3, as reported in this table, with the overall WRMS of ERP residuals reduced by something like around 20% for all ERPs. Here are the combined geocenter coordinates in the daily combined repro3 solutions. The red lines are the low-pass filtered repro3 geocenter motion estimates. And the blue lines are an SLR-derived seasonal geocenter motion model from John Rees. As for the seasonal variations in X and Y, the repro3 estimates are generally in phase with SLR, but have smaller amplitude in X and larger amplitude in Y, which is again similar at what we saw in repro2. And like in repro2 again, the Z component of the repro3 geocenter motion estimates is still swamped by draconic errors. But unlike in repro2, the near annual variations in Z are now also mostly in phase with SLR, which seems to be a progress and might be attributable to better solar radiation pressure models in repro3. And to conclude this part, let's finally look at the scale of the daily repro3 combined solutions. For scale factors estimated between the daily combined repro3 solutions and the IGS R3 reference frame are shown here in black. And they were modeled here as the sum of a linear trend plus periodic variations in red, of overload noise in pink, and of variable white noise in turquoise. The estimated linear trend with respect to the IGS R3 reference frame is basically 0. But if we add the transformation parameters between that frame and ITRF2020, then we get a scale offset of 7.6 millimeters and a drift of 0.2 millimeter per year between IGS repro3 and ITRF2014. I won't comment on that so much because there will be a whole presentation on that topic by Suzanne later in this webinar, and Zoe will also talk about that. But I would just like to mention that while the 7.6 millimeters offset is controlled by the calibrations of the Galileo satellite antennas, the 0.2 millimeter per year drift is not. Actually, this drift is controlled by the assumption which is made in every IGS Antex file that satellite ZPCOs are constant with time. And the same drift of 0.2 millimeter per year was already there between repro2 and ITRF2014. So that's it for the repro3 SINEX combination results. And in the second part of this presentation, I would now like to show results from preliminary comparisons that I made between the IGS repro3 station position time series and station position time series from other sources, namely the ones from the TU Graz contribution to IGS repro3, the IGS repro2 station position time series, as well as two other widely used station position products, which are the PPP series from JPL and those from the Nevada Geodetic Laboratory, NGL. So what I did for each station among a selection of 215 well-behaved reference frame stations was to remove post-seismic deformation models when necessary, then adjust the same piecewise linear plus annual plus semi-annual model to the 5 time series and compare the 5 residual time series. You can see here an example of such residual time series for a station in Chatham Island, New Zealand. It's quite hard to tell with the naked eye which are more or less scatters, but there are actually scatter differences, and those can be quantified, for instance, by relative WRMS reductions from each of the other series to the repro3 series, such as shown here in these maps. So every time a station is read in these maps, this means that its repro3 series is less scattered than its TUG or IG2 or JPL or NGL series. And well, all the maps are either frankly red or at least reddish in average, which means that the repro3 series are the less scattered in average. And it's nice to notice an average WRMS reduction of around 8% in east and north and around 5% in up from repro2 to repro3. We can also look at those residual time series in the spectral domain. Here are their average periodograms, but the picture is clearer if we look at differences between the average periodograms or actually between their square roots. such as shown here. So all the differences are taken with respect to the IGS repro3. And negative values mean more power in the repro3 series, while positive values mean less power in the repro3 series. And it's nice to see positive values practically everywhere. In particular, the background noise appears to be smallest in the repro3 series, while it is largest in the PPP series, considered in this comparison. And all of the periodic errors are also, no, not all, but periodic errors are also generally smallest in the repro3 series, except of course for the GLONASS related 8-day signals, which are obviously absent from GPS-only series. And again, it's nice to note a reduction of draconic and fortnightly errors from repro2 to repro3. And that's all I had to show. So I will skip this summary slide and move to the next steps. So I'm currently identifying all of the discontinuities in the repro3 station position time series and also deriving new updated models of post-seismic displacements. That's a long and tedious work, but which is essential both for the preparation of ITRF2020 and also for further studies of the IGS repro3 station position time series. And next, well, I would like to answer all of the questions that were raised during this presentation, investigate the apparent higher precision of TUG solutions, investigate the inter-AC station position biases, such as the ones seen for the station in KC, Antarctica, and extend that comparison of station position time series that I just showed to more stations, all AC contributions to repro3, and analyze the results in more detail. And that's it. Thank you very much for your attention.
Thank you so much, Paul. We have a couple of questions, actually 4 to be more specific. So the first one, 5. So the first one comes from Jose Antonio Dario, and the question is it expected that the new strategies used in repro3 will have a recommendation from the IGS for the calculation of continental regional reference frames?
Well, it is generally advised that users of the IGS products use the same standards that were used for the generation of these products. So yes.
Okay. Second question comes anonymous. Why does a TUG perform so well in comparison to the other ACs? Example on slide 8.
Yeah, that's a good question for which I don't have the answer yet. Well, TUG use a brand new software. They use different strategies as the other analysis centers, what they call the raw observation strategy. Instead of making double differences, they use 0 differences. Other ACs do that, but TUG also use the raw L1, L2, L5 observations instead of making iono-free combinations. So that might hold a part of the answer, but I'm not so sure that it can explain the apparent better precision of TUG during the old GPS-only period of repro3. Another thing that might explain the better performance of TUG could be their special strategy for the weighting of observations. They use, I think they use a, well, I don't really know the details, but that needs to be further investigated and together with the colleagues from TU Graz. And I don't know, maybe Sebastian Strasser could add a word to what I just said. I saw he's here today.
Okay. All right, moving on, just so you know, the Q&A, it's going to be open. I'm going to leave it open so you can continue answering these questions and have further discussions after the presentation. But I'll move on to the third question. So that is from Sergey Prudenko. What are the criteria to include GNSS stations in the combined IGS solution? Will all stations provided by ACs be included? Is there an IGS recommendation list of stations to be processed by ACs? Thank you.
All stations that were processed by any AC are intercombined solutions. There was no exclusion at all. But before repro3, there was a list of recommended stations for the ACs to process, including IGS reference frame stations and collocated stations, stations collocated with other space geodetic techniques, and then other levels of priorities, like stations that were of interest for the regional reference frame subcommissions, etc.
Okay. Next, from Tom Herring, do you know why number of stations by multi-ACs drop off after 2015-2017?
No, I don't know.
Okay, next question. Are the repro3 products, orbit, clock, etc. available?
Not yet. Not yet. That's a question that should be asked to Salim later.
Okay, and we have here, as from Hambingham, as to the ground antenna calibrations, is only chamber, robot, or both of them are used?
The repro3 on text files only includes robot calibrations, with one exception. An antenna type for which we had a multi-GNSS chamber calibration available, but no robot calibration available. So it's basically robot only.
Okay. And one last question before we move on, from Emily Klein. Thank you, Paul, for your presentation. What is your strategy to model the post-seismic displacements?
Like in ITRF2014, this will be done by the estimation of exponential and or logarithm functions on a station by station basis. So for each station with apparent post-seismic deformation, we will fit the exponential and or logarithm model that fits the data better, like in ITRF2014.
Okay, well, thank you very much. We're going to move on.